Whether or not aliens exist in our universe has been one of the most crucial and thoughtful debates in human history, and there are so many arguments for both sides, and today I am going to cover pretty much every argument against alien life. Now, their order of appearance in this video I am ranking by how strong I find them to be, starting with the least strong ones and getting into the ones that could, change somebody's mind. So yeah, let's get into this. Subscribe to the channel. Most importantly, according to this graph, only 1% of you are subscribed, which is ridiculous. That sounded too believable. That wasn't. According to this graph, actually, nobody is subscribed, so we need to fix that. But also follow my Instagram and join the Discord, links in the description. Let's get into the first argument. First, we have the early universe was hostile to life. The core idea here is pretty simple. The universe did not start out as a place where life, especially complex life, could realistically exist. Right after the Big Bang, the universe was basically just hydrogen and helium, plus radiation everywhere. All the stuff life needs on Earth, carbon, oxygen, nitrogen, phosphorus, metals like iron and magnesium, had to be cooked later inside stars and then scattered into space when those stars exploded. That process takes time. Stars have to form, live out their lives, go supernova, and only then do they enrich the surrounding gas clouds with heavier elements that can build planets, atmospheres, oceans, and eventually life. Because of that, the very early universe was metal poor in astronomy terms. Fewer heavy elements means fewer rocky planets and fewer Earth-like environments. Even if a planet could form, it might lack things like a solid crust, a stable atmosphere, or enough chemistry to support anything beyond very simple hypothetical chemistry experiments. On top of that, the early universe was much more violent. More frequent gamma ray bursts and supernovae in young star-forming regions would have been blasting planets with sterilizing radiation much more often than today. So even if life tried to get started, it would be constantly exposed to big catastrophic events that could wipe it out or reset everything. And this one ends up being at the bottom of the list because it's almost comforting once you sit with it. Like, instead of saying aliens don't exist, it just says they might show up late. If the early universe was chemically poor and full of violent radiation, that's a very temporary condition on cosmic timescales. Stars age, metals accumulate, gamma ray bursts become less frequent, and the environment gradually becomes more forgiving. Like, an optimist can look at that and say, okay, so the first half of the universe's life was a write-off, but the second half might be where everything actually happens. It also does not directly contradict any of the classic sci-fi hopes. You can still imagine galactic civilizations, ancient alien ruins, or crowded star systems, and you just move all of that into a later window where the chemistry and radiation environment are better. So compared to other ideas that we're going to get into later on, this one barely touches the core belief that life could be common. It just says not at the beginning, which makes it one of the least damaging for people who want to stay optimistic. So next we have technological civilizations may be brief. This argument says that even if technological civilizations do arise in the universe, they may not stay technological and detectable for very long. There is a short window between when a society learns to harness large amounts of energy, build radios, lasers, or starships, and when it either destroys itself or changes into something much quieter. While in that window, it is loud in a way that other civilizations could notice. Outside that window, though, it might be extinct, collapsed back to a pre-technological state, or transformed into a form that barely interacts with the outside universe. The self-destruction side of this is the most obvious. As soon as a species gains advanced technology, it also gains powerful ways to kill itself. Nuclear weapons, engineered pandemics, uncontrolled artificial intelligence, extreme environmental damage, and runaway climate change are all examples where a civilization could knock itself down in a relatively short amount of time compared to cosmic timescales. Even a few hundred or a few thousand years of dangerous experimentation is nothing compared to the billions of years a star lives. universe. So one version of this argument says that most technological societies flicker on, experiment with dangerous tools, and then wipe themselves out or cripple their ability to maintain high tech. There's a quieter version that does not require global catastrophe. A civilization could simply lose interest in broadcasting, exploration, or wasteful megastructures. It might move into very efficient, low-energy computing, use tight beam communications that are almost impossible for outsiders to intercept, or retreat into virtual realities and local concerns. From the outside, that looks similar to extinction. You wouldn't see big radio beacons or obvious engineering projects. The civilization still exists, but its detectable signature is tiny compared to the background noise of space. So the reason that this one doesn't rank super high on the scale is mostly that it attacks timing, not existence. It even kind of posits the idea that civilizations do exist, but they just don't stay like loud for very long. So this one actually kind of admits alien existence. And if you're optimistic, this is actually pretty easy to spin into a coping story. You can say, we're early in our tech phase. They might be far ahead or far behind, and we just haven't overlapped yet. Or most species grow up, stop screaming into the void with omnidirectional radio, and switch to efficient narrow communication we can't detect. It definitely explains the lack of contact, but it actually posits that aliens probably do exist. So yeah, this one is really not that good of an argument, but it is more interesting and more compelling than the ones before it, in my opinion. So let's move on. Now we have the non-convergence of intelligence. Shit, dude, saying that out loud, it sounds like a Star Trek movie or something, like a shitty one. This argument starts from a simple observation. If intelligence were the natural end goal of evolution, you would expect it to show up over and over again in different lineages. But on Earth, it really did not. Life has been here for billions of years. Complex multicellular life has been around for hundreds of millions of years. In that time, with all those ecosystems and all those different branches of the tree of life, you get exactly one species that builds radio telescopes and rockets. You can find clever behavior in lots of animals, but full symbol-using, tool-making, technology-building intelligence in the way we mean for aliens is basically a single accident. Evolutionary biology already has a framework for this. Natural selection is not aiming for a specific outcome. It does not care about higher or lower. It rewards whatever works in that specific environment at that specific time. Jellyfish, crocodiles, beetles, and bacteria are all doing great without language, algebra, or space programs. From a cold evolutionary perspective, a human brain is an extremely expensive piece of hardware. It burns a lot of energy, it makes childbirth dangerous, it requires long childhoods where offspring are helpless, and it depends on complex social structures to function well. None of that is inherently better in the survival sense than just being a simple, efficient organism that just eats, reproduces, and does not waste calories on abstract thought. On top of that, the fossil record shows multiple moments where life had a chance to try something different and still did not converge on intelligence. There were huge, diverse ecosystems in the oceans long before land mammals. There were dinosaur-dominated worlds with large, active species and complex behaviors. There were repeated bursts of new body plans after mass extinctions. In each of these eras, many lineages became successful without turning into anything like a human. The one time you do get a lineage that takes the weird path of big brains, hands that manipulate objects, culture, and cumulative technology, it happens late and only in one branch. This argument sits in a pretty balanced spot in terms of strength. It has some real weight because it's grounded in direct evidence from Earth. When people point to non-convergence, they are basically saying, look, we have a planet with ridiculous biodiversity, hundreds of millions of years of complex ecosystems, and only one lineage ever gave us this level of intelligence. That's a legit pattern in the data, and it pushes back against the casual assumption that brains like ours are some kind of natural finish line. At the same time, though, it's not really a good argument for this in one sense, because it leans heavily on a sample size of one. Critics can can fairly say that we just don't know how evolution behaves on different planets with different chemistry, different climates, or different starting conditions. Some people point to crows, parrots, dolphins, octopi, and say there are multiple almost there cases that might have gone further in a slightly different world. Okay, pausing, can you imagine a world where dolphins or octopi or crows became like an intelligent species like us? Dude, that's crazy. Anyway, so the argument has enough evidence to make people cautious about assuming every biosphere spawns a technological species, but it doesn't have enough to prove that we're nearly unique in the whole galaxy. So this argument does chip away at the idea that intelligence automatically emerges given enough time, but it still leaves a lot of room for other planets to roll the dice differently. It is strong enough to change how you picture a life-rich universe, but also, again, like, our Earth is pretty young, all things considered, and this is only arguing against intelligent life, not aliens in general. So let's move on. Next up, we have no evidence of past visitors argument. This argument is basically, if advanced civilizations exist and interstellar travel is at least somewhat doable over long timescales, then you would expect at least one of them to have reached Earth at some point in its multi-billion year history. Not necessarily now, and not necessarily with flying saucers in the 1950s. I mean, that was proved to just be the Planet Express ship, but at some point in all that time. And if that had happened, they should have left something behind that is clearly not natural and not human. A piece of tech, a structure that doesn't fit any known culture, strange isotopes, artificial artifacts in old strata, anything that screams, hey, this was made by someone else. But when you look at archaeology, geology, and planetary science, you don't see anything like that. Checkmate, Christians. The strength of this argument comes from how old and exposed Earth is. The planet has had stable surfaces, oceans, and atmosphere for billions of years. Complex life has been around for hundreds of millions of years. The solar system itself is not hidden. We are on an ordinary star in the galactic disk, not buried away in some weird, hard-to-reach location. If interstellar exploration is even moderately attractive for advanced civilizations, you would think that at least some probes, expeditions, or automated machines would have swept through systems like ours. And if you have millions or billions of years to work with, you don't need fast starships. Even very slow, creeping exploration could still fill the galaxy. On top of that, we are very good at finding weird things in the ground. Human archaeology has dug up tiny tools, bones, and structures and waste from all kinds of cultures going back tens of thousands of years. Geology has uncovered layers from hundreds of millions of years ago, with detailed fossils and chemical traces. Planetary scientists study meteorites, sediment layers, and isotopes to track everything from old mass extinctions to asteroid impacts. All of that means that if there ever had been a clearly artificial object made of unfamiliar materials with advanced machining or strange isotopic signatures from long before humans, it would stand out immediately. The fact that nothing like that has turned up suggests nobody has been here, at least not in the way that left durable traces. And this argument also feels strong because it lines up with how we treat our own artifacts. Human junk lasts. Roman concrete, old tools, plastic in the ocean, radioactive signatures from tests in the 1900s, all of that sticks around. Scale that logic up to an advanced civilization, and people naturally assume their stuff would be even more durable or weird looking. So no past visitors, this argument hits that intuitive part of your brain that expects long-term traces from big actions. On the other hand, it's not bulletproof. The entire thing rests on a bunch of assumptions stacked together. That interstellar travel is doable enough that lots of civilizations would try to attempt it, that they would actually choose to visit random biospheres instead of focusing on closer or more useful targets, that they would build or drop things that would last tens of millions of years, and that we would have already looked in the right places with enough detail to notice. As soon as you start poking those assumptions, the argument looks less like a slam dunk and more of a supporting argument, is how I see this one, at least. Like, it's kind of a self-confirmation bias where either side can point to this and say, hey, that supports our side. But let's move on. Next up, we have no astroengineering signatures. So the starting point of this argument is the Kardashev scale idea. So if a a civilization gets very advanced, it might start using energy on the scale of an entire planet, which is type 1 civilization, an entire star, which is a type 2 civilization, or even a galaxy, which is the type 3. To do that, it would need huge infrastructure. The classic example is a Dyson sphere or Dyson swarm around a star, a bunch of structures collecting starlight and converting it into usable energy. And with this, you don't have to guess their language or motives here. Physics says that if you capture that much energy, you cannot make it disappear. Some of it has to come out like as waste heat. So people realized you could search for aliens not by listening for radio messages, but by looking for stars and galaxies whose light looks wrong. If a star is mostly surrounded by collectors, its visible light would be dimmed and a lot of its energy would be re-emitted at infrared wavelengths as heat. A galaxy full of these projects would show up with a weird infrared profile too. We don't need them to want to talk or to aim anything at us, we just have to look for unnatural looking energy usage in large surveys of stars and galaxies. Over the last decades, astronomers have used infrared telescopes and sky surveys to do exactly that. They have looked for stars with strong infrared excess that does not match dust clouds or normal astrophysical processes, and for galaxies that are strangely dominated by mid-infrared output. There have been a few odd candidates, but every time someone digs deeper, the weirdness usually turns out to be dust, active galactic nuclei, or other known phenomena. Nothing so far has screamed, "This is a star wrapped in machines," or anything like that. That negative result is where the sting comes from. Before these searches, people could say maybe aliens are out there but don't broadcast, or their signals don't overlap with our time, or they prefer tight beams that we don't catch. Astroengineering was supposed to be the workaround. Even if nobody talks, a galaxy packed with super advanced civilizations should not look completely normal like a normal galaxy. If you imagine lots of type 2 or type 3 civilizations transforming their environments, then the sky should have some obvious outliers, and those outliers have not really shown up. At the same time, the argument isn't as simple as we don't see Dyson spheres, therefore there are no advanced aliens. There are a lot of assumptions baked in. One is that civilizations actually want or need to push to those energy scales. Maybe most of them focus on efficiency instead of raw consumption, with very compact infrastructure that doesn't distort their stars in any dramatic way. Another assumption is that they build things in the specific ways that we imagined, like shell swarms that re-radiate in wavelengths that we're looking at. They might use different materials, different geometries, or different energy sources that don't produce an obvious infrared excess. It's also possible that the fraction of civilizations that reach that level is small, or that they don't last long enough for us to catch them in surveys. You also have the practical side. Our searches are wide, but they're not perfect. There are limits in sensitivity, coverage, and astrophysical noise. Dust, gas, and normal galactic activity can mimic some of the signatures that we're looking for, which makes it hard to declare anything definitively artificial. So the lack of a clean detection is meaningful, but it's not the same as a formal proof that no one anywhere is doing some kind of large-scale engineering. But now we're getting into the next one, which is the Drake equation collapse argument. Okay, so the Drake equation originally wasn't meant to be a magic formula that proves aliens exist. It was basically a structured way for people in the 1960s to sit down and talk through all the steps between there are stars and we detect a civilization. If you're on YouTube or on the Spotify video, you can see on screen the equation right now, and it's pretty confusing, but basically you break the big question into smaller questions, like how many stars form, how many of those have planets, how many of those planets could host life, how often life actually starts, how often it becomes intelligent, how often intelligence builds tech that we can detect, and how long that tech phase lasts. In the early days, people would plug in values that were, let's say, friendly to the idea that we're not alone. You might assume quite a few stars formed every year in the galaxy, assume a decent fraction had planets, assume on those planets a fair number were in the right zone for liquid water, and then quietly treat the life starts and life becomes intelligent steps as if they were not super rare. On top of that, you'd imagine that once a civilization gets going, doing, it stays on the air for a long time. Put it all together and you get versions of the story where the galaxy probably has lots of neighbors. The slow deflation started when people stopped treating those middle terms as easy wins. So on the astronomy side, exoplanet science did actually confirm one of the optimistic guesses. Planets are common. Surveys like Kepler and others made it clear that many, maybe most, stars have planets. And that sounds like a big yes for alien optimism. But as we learned more, the picture got messier, and this is where we get into the collapse that this whole argument is based on. A lot of undiscovered systems look nothing like our neat inner rocky planets plus outer gas giants arrangement. There are systems with big planets very close to their star, systems where orbits are eccentric, systems where gravitational interactions can easily destabilize things over long periods. So lots of planets stayed true, but lots of stable Earth-like long-term habitable planets started to feel more like a specialized category rather than the default. Meanwhile, origin of life research refused to give anyone a clean answer. The fraction of potentially habitable worlds where life actually appears is one of the key terms, and we still do not have a universally accepted mechanism that turns simple chemistry into the first self-replicating systems. There are multiple competing ideas like hydrothermal vents, warm ponds, mineral surfaces, etc. There are multiple interesting lab experiments and plausible paths, but no single agreed "this is clearly how it works" pipeline. That doesn't mean that life is rare, but it absolutely undercuts the casual assumption that it's almost guaranteed to pop up whenever conditions are okay. Then there's the how often does life become intelligent and technological question, which is where all that stuff we talked about with non-convergence comes in. Earth had billions of years of evolution, and only one lineage became a civilization-building species. That doesn't give us a precise number, but it does make people more cautious about pretending that intelligence is a natural outcome everywhere. So instead of plugging in a confident high value for fraction of life worlds that evolve technological species, a lot of scientists now treat that term as wildly uncertain. The how long do civilizations stay detectable piece has also gotten shakier. In the 60s and 70s, it was easy to imagine thousands or millions of years of radio broadcasts, big engineering projects, and obvious tech. Over time, people realized there are many ways that visibility could be short-lived. A civilization might destroy itself. It might switch to much more efficient, tight beam communication that barely leaks anything into space. It might move into infrastructure that does not stand out much from natural processes. The net effect is that the number for lifetime detectability went from "let's just assume it's pretty long" to "we honestly have no idea, and it could be very short on cosmic timescales." So, when people talk about the Drake equation collapsing, they don't mean the formula stopped working. The equation itself is just a way of organizing questions. What collapsed is the habit of plugging in one optimistic guess for each step and treating the output as a reasonable estimate for how many civilizations exist. Today, those middle terms are treated more like ranges. This might be extremely rare, or it might be fairly common, and we don't have enough data to say. That means when you multiply them together, you don't get a tidy answer like n is 10,000. You get something like n could be much less than one in the whole galaxy, or it could still be a large number, and our current knowledge simply doesn't pin it down. And this is an argument against alien existence because for a while people used the Drake equation as a thing to prove alien existence. New mic, guys. But now we just know that that's not really a good argument for it. So a lot of the people who were using the Drake equation to remain believing in aliens now might gotta rethink that. But next, let's get into the next argument, which is the anthropic bias argument. So this idea is basically when you look around and see that you live on a nice, life-friendly planet in a universe that seems hospitable to life, that observation is automatically biased. You're only able to notice anything at all from the places and conditions where observers like you can exist. You never get to see all the failed runs, all the sterile planets, all the universes where nothing interesting ever made it to the point of asking questions, because by definition, there's nobody there to notice those things. In the alien life debate, this hits a very specific assumption people make without thinking about it. A common line of thought goes like this. Look at Earth. Life appeared quickly once conditions were right. The universe's physical constraints allow chemistry, stars, long-lived stable systems. That must mean life isn't super rare. But then this anthropic bias we're talking about comes in and says, hey, careful. You weren't always gonna find yourself in one of the few spots where this works. That doesn't tell you how common these spots are overall. You can think about it like this. Imagine a gigantic lottery where almost all tickets kill you instantly, but one ticket lets you live and look around. If you're here thinking about the lottery, it means that you pulled one of those extremely lucky tickets. And from your point of view, you're standing on the life-friendly result. But all the people who didn't get that aren't around to show you that there are other options. You know what I mean? It doesn't give you any new information by itself about how many bad tickets exist. It just tells you the minimum. At least one good ticket was possible because you're here. There could be a million like it, or there could have only been that one. Your perspective can't distinguish between those cases just by saying, well, I survived. And so applied to the cosmos, anthropic bias says, of course you find yourself on a stable planet with the right chemistry around a calm enough star in a region of the universe where things aren't constantly being sterilized. If you weren't in a niche like that, you wouldn't be having this conversation. So the fact that your environment is surprisingly finely tuned to your existence can't be taken as strong evidence that such environments are common. It's just a necessary condition for you to exist in the first place. So it doesn't really defeat the argument, but it definitely puts some holes in it. Anyway, moving on. And I'm not even saying my opinions here, guys. I'm just, having a theoretical, objective debate. But this messes with the way that people use Earth as a typical example in the alien conversation. For a long time, both in popular science and casual conversation, there's been this vibe of like, Earth is one sample drawn from the universe and life happened here, so it must be pretty easy for it to happen. Like the universe is so big, if it happened once, it's gotta happen so many times. And anthropic thinking says Earth is not a random sample, it's a highly specific chosen conditional sample. Like you picked the one ball from the bag that already had observers exist here written on it. That makes any naive frequency estimate built from that one ball really shaky. And like I said earlier, I went off script earlier, I forgot that I put this in the script, so I'll kind of breeze through this. But this interacts with the fine-tuning list that people make about the right strength of gravity, the right types of forces, the right range of physical constraints, the right random breaks in evolution, etc., etc. Without anthropic bias, you look at that and say, wow, all of this suggests that the universe is designed for life. But then with the anthropic bias, you instead say, only in places where all those conditions line up can anyone even sit here and remark on it. Everywhere else, there's just nobody to talk about it. There's nobody to complain. In the context of aliens, again, the strength of this argument is how quietly it undercuts a big chunk of we're not special reasoning. It doesn't claim that life is rare or common, it just keeps reminding you that using our own existence as evidence for frequency is dangerous. And that's why this is the first one on this list that I think truly is a really good argument. It's not proving anything, but it definitely cuts the legs off some arguments on the other side. But we're not even, well, I think this is halfway actually. We're halfway through the arguments. So let's get into the next one, the evolutionary bottleneck argument. So with this argument, you start with the fact that Earth has been habitable for a long time. Liquid water and decent surface conditions go back on the order of billions of years. Life shows up relatively early in that window in the form of simple cells, but then there's just this huge stall. For most of Earth's history, everything is microscopic. No brains, no tools, just an enormous amount of time spent as bacteria and other simple organisms. The big transitions take forever. Complex eukaryotic cells show up late compared to the start of life. Multicellular organisms with specialized tissues show up even way later than that. Nervous systems and complex body plans come after that. Large animals, land ecosystems, social behavior, all of it is piled toward the back half of the story. Then you zoom in further and realize that actual technological intelligence, the kind that builds radios and telescopes, is only a thing in the tiniest sliver right at the end. Homo sapiens are a blip, and modern civilization is a blink inside that blip. I heard it described to me this way by my biology professor, who, shout out, he was great. He said that if life on Earth was compressed into a 24-hour day, by the same scale, humans would only be in the last 1 second second of that day. And at the same time, Earth's habitable window is not infinite. The sun slowly brightens, climate feedbacks can break, oceans can evaporate or become unstable on very long timescales. Depending on how you model it, we may have something like a billion or so years of good surface conditions left for complex life. Maybe less if you're strict about what habitable means. When you line that up with the evolutionary timeline, you get this weird picture where intelligent technological beings appear very, very late in the game. Not early and not halfway, but a lot closer to the end, a lot closer than you might naively expect. The bottleneck argument is basically that pattern might not be a coincidence. It might mean that the steps required to go from simple life to something like us are genuinely difficult and time-consuming, even on a planet that's doing almost everything right. The planet has to stay stable long enough for multiple rare transitions to happen in sequence. If any of those transitions is slow, finicky, or dependent on a chain of lucky breaks, then most planets will simply run out of time. Their stars age, their climates shift, their oceans boil or freeze, or something goes off the rails before a technological species ever appears. You can think of it like a long obstacle course on a timer. Simple life clears the first hurdles pretty easily, then gets stuck on a series of harder obstacles in the middle. Earth barely finishes the course before the timer runs out. In that picture, a lot of other worlds start the race, get some kind of biology going, maybe even get multicellular life, but never make it all the way to the point where something is building radio telescopes and thinking about the cosmos. So they don't have to fail at the first step, but they can fail anywhere in the middle as long as it's not at the very end. This argument is really strong. The only, thing that I don't like about it again is that it only argues against intelligent life. But I mean, when we talk about aliens, that is basically what we're talking about, right? So this is still a really, really great argument. But the next argument I want to talk about is the early appearance of life counterintuitively hurts optimism argument. Okay, it's not the prettiest name, but it's a good argument. So this argument comes from one basic fact, and that basic fact is that life on Earth seems to have appeared pretty quickly after the planet became even vaguely stable. Once you had oceans and a cooler crust, you don't see a gigantic delay before the first signs of microbes show up. For a long time, people took that as a very pro-alien detail. If life starts fast as soon as conditions are okay, then maybe life is easy and it should pop up all over the place. The twist here comes when you line that up with how long it took to get from simple cells to anything like us. Like I just talked about in the last argument, evolution from microbes to complex multicellular life, then to big brains and technology, eats up almost all of Earth's habitable window. If any of those steps had started much later, there is a decent chance the sun's gradual brightening and climate changes would have cut things off before a technological species ever appeared. So in that light, life started early here doesn't necessarily mean life is easy. It might just mean that on the rare planets where a technological species appears at all, life basically has to start early, or there isn't enough time for the rest of the story to play out. If life starts late, those planets never get to the observers asking questions stage. And that's where the counterintuitive part kicks in. Our early start can be read as a sign that life is common, but it can also be read as a sign that we're on a very lucky timeline. The kind of planet where things kicked off unusually fast, which is exactly the kind of world you'd expect any observers to be sitting on. It doesn't prove life is rare, but it definitely weakens the old habit of treating, oh, life appeared early here, as a straightforward evidence that it must be easy everywhere. So, next argument is abiogenesis might be near impossible. And guys, now we're in the top 5. We're getting into the really, really strong ones, the really good ones. And I hate to do this, but if you're still here, subscribe, bro. Come on, let's get some more subs. Let's get some more people up in here. Thank you, and let's move on. So, this argument, abiogenesis is just the name for that jump from non-living chemistry to the first self-replicating evolving life. Before that point, you just have a planet covered in molecules reacting, rearranging, forming chains, breaking apart again. After that point, you have something that can copy itself, mutate, and eventually turn into all the crazy diversity that we see in biology. So abiogenesis is just life starting. And the whole debate here is about how easy or hard that initial leap is. For a while, people were pretty casual about treating it as probably not that bad. Life on Earth shows up early in the geological record, which makes it tempting to imagine some natural pathway from simple molecules to primitive cells that just kind of happens once conditions are right. Warm little ponds, lightning, hydrothermal vents, UV light, you name it. The story in people's heads was that the universe has lots of chemistry, so given enough wet rocks, life will just sort itself out. But the deeper origin of life research goes, the more tangled that story looks. You quickly run into problems like, how do you get long information carrying molecules like RNA or something similar to form in realistic environments without falling apart? How do you keep those molecules concentrated instead of being diluted in the ocean? How do you get a system where replication is accurate enough to preserve useful information, but not so rigid that evolution can't happen? How do you wrap all of that in some sort of membrane or compartment and keep it powered in a way that doesn't just rip it apart? Researchers have come up with a bunch of partial answers. There are experiments that show bits and pieces. Certain minerals can help assemble chains, lipid-like molecules can form little bubbles, some simple systems can copy short strands under lab conditions. You get these glimpses where a part of the puzzle seems promising, but there's still no single, widely accepted, full sequence that takes you all the way from early Earth environment to a robust, self-sustaining, evolving protocell in a way that most experts agree is realistic. And that gap is what gives this argument its weight. Every time you think there might be a straightforward route, you run into new requirements, size conditions, or failure modes. The more precise the chemistry gets, the more it looks like you need a very specific set of circumstances, maybe even a series of lucky alignments to make it actually work. If that is true, then life might not be something that pops up on most habitable planets. It might be something that happens only under extremely rare, extremely special combinations of environment, timing, and chemistry. What really bothers people who follow this line is that scientific progress has not been slowly turning abiogenesis into a solved, routine process. Instead, it keeps revealing how many things have to line up correctly. We have more ideas, more models, and more experimental tricks than ever, yet the "this is definitely how it happened" story remains out of reach. That doesn't prove that the jump was near impossible, but it keeps the door wide open for that possibility, instead of closing it. In the context of alien life, this means you can't safely assume that every Earth-like planet with water automatically gets biology. If the initial spark is extremely hard, you could have a universe full of planets that are chemically ready for life and never quite made it past the starting line. From far away, they would look like good candidates, but they would just stay empty. That picture is very different from the old assumption where life is almost guaranteed to appear wherever it can. And the more origin of life research circles around without locking down a clear, robust path, the harder it is to dismiss that near impossible option as just pessimism. But next up, we have the rare Earth hypothesis. So at its core, this argument says simple life might be fairly common in the universe, but complex animal-level life, like what we have here, depends on a long list of specific conditions lining up together. Not just liquid water and a rock at the right distance, but a stack of geological, astronomical, and chemical factors that all have to cooperate for billions of years. People who talk about rare Earth usually point to things like the star. You want one that's not too big, short-lived and unstable, but also not too small, tidal locking with nasty flares. You want something calm and long-lived like the sun. You also want a pretty stable, nearly circular orbit so the planet doesn't swing between freezing and boiling every year. Then there's where you sit in the galaxy. Too close to the galactic center and you get more radiation, more supernovae, more gravitational chaos. Too far out and you might not have enough heavy elements to even build Earth-like planets. On top of that, you want plate tectonics to recycle carbon and keep the climate in a workable range over deep time, plus a strong magnetic field and atmosphere to shield the surface from charged particles and high-energy radiation. The moon shows up in this story too. A big moon helps stabilize the planet's axial gravitational tilt, keeping seasons within a reasonably stable range instead of wild, chaotic swings that could constantly trash climate patterns. And the layout of the rest of the system matters. Gas giants like Jupiter and Saturn in the right places can help divert or soak up some of the comets and asteroids that might otherwise hit the inner planets, without constantly destabilizing everything. Even if you grant all that hardware, you still need timing and biological luck. And this hit at a really specific moment in the alien life conversation. For years, people leaned on the sheer number of stars and planets as a comfort blanket. So many rolls of the dice, something like Earth must happen a lot. And then those exoplanet discoveries confirmed that planets really are common, which sounded like a win, but then this hypothesis slash argument kind of came in and said, hey, it's a lot more than just that. But I'm not going to spend too much time here because most of this is kind of like just a amalgamation of a lot of other arguments I've already talked about. This is just a strong version of all of them together. So let's get into the next one, the Great Filter. So this argument starts from a weirdly simple place. If the universe is old, big, and full of planets, why isn't it obviously full of civilizations? The Great Filter says there must be one or more steps on the path from dead matter to galaxy-spanning civilization that are insanely unlikely or hard to survive. So imagine a line of steps that go from habitable planet to life to complex life, and then to intelligence, and then to technology, and then to long-lived spacefaring civilization. So imagine all those steps as hurdles lined up on a track. The Great Filter argument basically says at least one of those hurdles is not just pretty tall, it's almost nobody ever clears this. Maybe it's the first appearance of life. Maybe it's the jump to complex cells. Maybe it's the emergence of intelligence. Maybe it's the ability to build advanced tech without wiping yourself out. You don't know which one it is, but you know there has to be a serious bottleneck somewhere. Otherwise, the galaxy should look very different than it does. But then, with this, it makes sense, right? But the scary part is the question of, is this filter behind us, or is this filter ahead of us? If the filter is behind us, that means one of the early steps was nearly impossible, and Earth just happened to get through it. Abiogenesis might be almost never achieved, like we were talking about. Or maybe the leap to eukaryotic cells, or the leap to multicellular life, or to something with human-level intelligence is vanishingly rare. In that case, the universe can be full of planets and even full of simple life, but almost none of them ever make it to civilizations that build radio telescopes. In that version, the silence out there is telling you that we already passed the killer hurdle, and most other worlds never did. But if the filter is ahead of us, the story is totally different. That would mean the early steps are not that unusual. Life might start pretty common, intelligence might emerge on a decent fraction of worlds, and a lot of civilizations might get as far as we have. But none of them make it through the later steps, such as surviving advanced technology without destroying themselves, avoiding permanent ecological collapse, not getting wiped out by something that they built and can't control, or not hitting some other unknown systemic failure. In that picture, the reason the galaxy is so quiet is because every civilization that reaches our level eventually hits the same wall and disappears. What really pressures optimism is how the Great Filter reframes future discoveries. If we dig up evidence of independently arising life in our own solar system, like a separate origin on Mars or in an ocean moon, that would suggest that the life from chemistry step is not that rare. And that sounds fun at first, but under Great Filter logic, it nudges the filter away from the early steps and closer to the later ones, which is not comforting. On the other hand, if we never find life anywhere else, not even fossils or simple microbes nearby, that leans toward the filter sitting at or near abiogenesis, which is bleak for the universe, weirdly reassuring for our long-term prospects. It also slots straight into the Fermi paradox. But let's move on. The next argument is called the universe may be mostly stillborn argument. Now, this argument is kind of the extreme version of abiogenesis is hard. It says the main reason that we don't see anyone out there is not because civilizations blow themselves up or decide to go quiet, but because almost no planet ever makes the jump from chemistry to actual life in the first place. planets, hence the word stillborn. You can have tons of rocky worlds with water, organics, and energy sources. They can run prebiotic chemistry for billions of years. But the specific chain of events needed to create a self-replicating, evolving system almost never happens. So most planets stay stuck as chemically rich but lifeless. And this one makes a lot of sense. Again, I'm not going to spend too much time here because we've already kind of talked about this, like all the evidence for it in other sections. But I mean, yeah, the fact that life even started at all is insane. But now we have, finally, the Fermi paradox. This starts with a really basic clash between two ideas. On one side, you have the scale and age of the galaxy. There are hundreds of billions of stars, many of them older than the sun by billions of years. We now know planets are common. So if life can arise, and if some fraction of that life eventually builds technology, it feels natural to think that there should be civilizations out there, a lot of them, and some of them should be far ahead of us. On the other side, you have the actual observations. The sky looks completely natural. We don't see any clear signs of megastructures. We don't receive unambiguous signals. We don't see evidence that anyone has been rearranging stars or leaving any kind of footprint. The Fermi paradox sharpens this by focusing on time and expansion, not just there are aliens. Even if interstellar travel is slow and imperfect, a civilization that decides to spread does not need magic. If you can send ships at a few % of the speed of light, and those ships can build new colonies that then launch more ships, you get a kind of wave that moves through the galaxy. Add in self-replicating probes and it becomes even easier. You don't have to cross the galaxy in one go. You just have to hop from star to star over and over again, and you have hundreds of millions or billions of years to work with. When you actually run rough numbers, the timescales feel almost insulting. The Milky Way is on the order of 100,000 light years across. Even expansion speeds as low as a fraction of a % of light speed can, in principle, fill the galaxy in something like 10 million to 100 million years. And that sounds huge in human terms, but compared to the age of the galaxy, it's nothing. The galaxy has had time for that kind of process to happen not once, but so many times over. If any civilization decided to spread in a visible way and did not immediately die out, the default expectation is that we would be living inside a galaxy that shows extremely obvious signs of that. Instead, everything looks untouched. And it's not just about like asking why we haven't heard a radio message or anything like that. It's asking why we don't see any of the side effects that long-term space-faring civilizations would plausibly produce, even if they never cared about us. Terraforming on a grand scale, obviously artificial structures, large-scale minings, terraforming on a grand scale, obviously artificial structures, large-scale mining stars, altered star distributions, weird energy patterns, anything that screams someone's been here for a long time. The Milky Way does not look like a tinted garden or an industrial zone. It looks like a mostly natural, unclaimed wilderness. Some people try to soften this in lots of ways. Maybe civilizations choose not to expand. Maybe they all live in simulations and ignore the outside world. Maybe they expand, but very quietly. Maybe there are self-limiting cultural presences that keep any species from spreading too far. Each of those is at least possible. The issue is that as you pile those escape hatches on top of each other, the original big numbers reasoning starts to turn on you. With so many stars, so much time, and so many different possible civilizations, you'd expect at least a few to break the pattern. Even if most species stay home or hide or collapse, you only need one that does not to make the galaxy look different. And that's why the Fermi paradox feels so corrosive to optimism once it clicks. It takes the same ingredients that used to make people confident that aliens were probably everywhere and uses them to argue the opposite. The more stars there are, the longer the time scales, the more chances for life to arise, the stranger it becomes that the galaxy is so quiet. You end up stuck between weird options. Maybe civilizations are incredibly rare to begin with. Maybe something wipes them out before they can expand. Maybe our intuition about how intelligent life behaves is badly wrong. None of those feel as comforting as the old space is big, they're just far away answer. And that's why the Fermi paradox is at the top of this list. And there are so many explanations to the Fermi paradox, answers to it. Guys, let me know if you want me to make a video about that. I would love to make a video going over all the explanations to the Fermi paradox. It's so interesting, but that marks the end of this video. Thank you all so much for listening and watching all the way through. You know, leave a 5-star on Spotify, subscribe, please, if you can. It would help so much. Thank you for being here though. Have a great night, everyone, and sweet dreams.